Okay, now it's starting? Fine. So, welcome to my presentation of processing of spatial sensor network data. And I like to start with a graphical representation of our problem we considered. It's also again about some spatial measurement. A physical field, for example, like humidity we had before, or temperature, or the concentration of a chemical pollutant in a lake. So we have our field, which is normally overlaid with a lot of noise, so we need a high number of sensor nodes to measure it. But if we simply forward all the sensor data, we have a lot of redundant information and waste of energy due to the communication. So the approach is to directly process the data inside the network to extract some key information, which we then send to the outside world. And with this key information, the user should be able to reconstruct the field and, for example, do some graphical display. So one remark, the focus of our work is on spatial compression, not on time series. I don't say that time series compression is bad, but only that there's already a lot of work, and here we want to go into another direction. Before I go to the algorithm, I want to start with the test data we used. We decided to use a synthetic data set, which gave us more freedom to test for different numbers of sensors, different noise levels, and we can change everything. Many authors use simple thermal diffusion process with point sources because that's mathematically very easy. But we decided to make it a bit more tricky and to be closer to physical reality. So we created our test data set by a computational fluid dynamics simulation. Here we were able to include other effects like the heat transfer by flows, so-called advection, and the influence of walls. So you're invited to download my test data set and run it on your own algorithm. And if you find a description of the field with even less parameters, then please let me know. Now, look what's inside. Very simple. It's a water basin with a small inlet and outlet to create a flow, and 3 disc-shaped heat sources, but it was complicated enough to give some work to the algorithm. And over this field, I randomly distributed between 100 and 500 data points. Now, last step before we go to the algorithm, how we can get the data in between. If we have data at random locations, we just get a cloud like in the small picture below, and it's very hard to make sense out of it. So it's better to transform it to a grid structure for graphical display, and for this we have to interpolate the field. I used the Kriging method because it's the best linear estimator. The interpolation is done by weighted average of the measurements. And the weights therein depend on a statistical function, the so-called variogram. And the variogram gives the expected value of 2 points, the expected difference between 2 points as a function of their geometrical distance. So let's go on. Now, the key idea of the algorithm. If we want to interpolate the field, we do not have to use all data points, all sensor points, for example, 200 is in my example. We can achieve almost the same result if we reduce the number of supporting points. For example, with only 25 supporting points, or virtual sensor as I call them, we got only a very little error compared to the full interpolation. So the question is now how to find the best or quasi-optimal locations for the virtual sensors. Typically, they are somewhere in between the real sensors. Mathematically, this leads back to an optimization problem. We have to find the locations which give us a minimum error for the interpolation, so the interpolation of all sensors and the interpolation of the 25 virtual sensors only. So far, this is only a central approach. Now we have to see how we can distributed inside the network. This happens if we separate our field into clusters. That's a quite natural approach because normally sensors cannot directly communicate with the base station. Normally you have cluster heads which collect the local data and then forward them to the outside. And now we can do all this virtual sensor approach directly on some cluster heads. I separated the field into 4 or 9 clusters, and each of the clusters is now compressing its local, the blue areas, interpolation into a new set of 6 virtual sensors. And I also did a second step of compression on a supercluster, where I then compressed the 54 received virtual sensors to a new set of 25 virtual sensors. Now, again, or going back into the optimization, how do I find the positions for the virtual sensors? I did a simple heuristic with a big advantage. It can be implemented on wireless hardware. It's starting with an evenly distribution set of virtual sensors, and then I optimized one by one their location, x and y coordinate separately. For example, for one point for x coordinate, I vary it by a small offset, plus minus x, giving me 3 points. For these 3 points, I calculated the total interpolation error, and then I got a minimum of this parabol, and this point I took as a new estimate for the location. And here in the graph, you can see how the points move during the optimization process if I repeat it for every point and both x and y coordinates. This approach I then tested on embedded hardware. I use the Sunspot sensor nodes from Oracle. They are equipped with a 400 megahertz ARM processor. They have 2.4 gigahertz communication and also a Java Micro Edition virtual machine, which made the programming very easy. I used them as the cluster heads and also as the end nodes, but the end nodes did not measure temperature as sensor nodes normally do. Instead, they played back the recorded data from the computational fluid dynamic simulation. And on the next level, for the supercluster, I tested both the Sunspot and the Raspberry Pi processor board. Now, let's have a look to the outcome. First question, of course, how accurate is the algorithm? First line I took as reference, if I do a central processing of 200 measurements, this I set to 0%. The network does nothing in this case, just forwarding all the data. Second step, if I do the compression to virtual sensors on the cluster head, then I got an additional error of 2%. Depends on the amount of noise you have on the measurements. Please go to the paper for the details, but in this case, 2% extra error is quite acceptable. And if I go one step further to the full in-network processing, when I also do compression on the cluster head, the error can go up to 9%, and if I'm doing some fast and reduced variant of the algorithm, error can even go up to 18%. That's a bad point, but the good point is the data compression we can achieve. The network internal communication we can reduce by a factor of 3.7, and the external communication we can reduce by a factor of 8 by sending only 25 instead of 200 sensors. So last question. Can we actually run this algorithm on embedded hardware? Let's see what happens on my platforms. I start with a supercluster. On the Sunspot, it was not quite satisfying. The optimization just for one measurement interval took more than 2 minutes. That's a bit slow. So I also tested the Raspberry Pi, which is a more advanced processor. That was less than 1 second, about 150 times faster. Both have an ARM processor, but different generation. So you can see it depends very much on the processor type, if they support floating point directly or not. And you can also see that energy is 33 times less with an up-to-date processor. So then look at the cluster head. They are tested only the sunspot because the Raspberry Pi is not really useful for wireless battery-powered applications. On the sunspot, the calculation for the cluster head took 3.7 seconds, which is quite acceptable. If you measure temperature, you normally do it in intervals of minutes or even longer, but energy consumption was still a bit high, was 0.33 joule, and compared with communication was a little lower, 0.3 joule, so it's still higher, and you gain nothing, because the algorithm should consume less energy, otherwise you cannot save anything by reducing communication. But I'm optimistic that this problem will be closed in the future if we have sensor nodes with some better or newer generation processors. As you see the difference between the sunspot and Raspberry, if we got new hardware, we will surely get to energy for calculation, which make it very interesting in comparison with communication. So let's come to the summary. So spatial data processing provides good data processing provides good compression, but we have to accept some little additional error. Okay, I hope I remember what I wanted to say. And it was, in the end, computational, much more challenging than we expected in the first place. But I think this will be solved by better processor or better embedded sensor hardware in the future, and then a network processing can do a very good job in reducing the communication in a network. Yeah, with this, I want to thank you for your attention.